Welcome back to Trigonometry. This is week 4 of our trig unit. We're today going to be connecting periodic models with what's called sinusoidal functions. Now we'll break down what this actually means as we look at our learning targets today. So first, we want to be able to determine the amplitude, period, and midline of periodic models. Remember, periodic models are those things like the Ferris wheel and other examples of periodic behavior, things which repeat themselves. Once we're done with that, we're going to identify the connection between those features of amplitude, period, and midline. And we're going to connect that with the equations of what we call sinusoidal functions. Now, sinusoidal functions are just any functions of the form sine or cosine. Because sine and cosine, which are the two functions we've been looking at more recently, because they're so similar, they kind of fall into one category, and we call those sinusoids. And finally, what we're going to do is we're going to derive periodic models using these functions. So we're going to create equations of sine functions, which can actually model these periodic behaviors. Before we get into all that, though, I want to do a quick review. We're going to do some trig evaluation. So let's suppose, for example, y'all, that we have been asked to evaluate these 3 trigonometric expressions. So I'm going to pull up my whiteboard, and we're going to give these a shot real quick. So on my whiteboard, I have my unit circle you can see there. And I also have this, Yes, I have my unit circle here, and I also have a little bit of an explanation of what is sine, cosine, tangent, cosecant, secant, and cotangent in terms of the x, y coordinates on the unit circle. I would strongly recommend keeping a unit circle in your notes on you, as well as these fractions, so that you can more easily evaluate trig functions. All right, y'all? So let's say I wanted to find the cosecant of negative pi over 4. So the way I'm going to do this, guys, is it's a negative. So I'm going to look at my unit circle, and I'm going to count backwards, actually. Right? So see how here's where 0 is. And if I take away 1 pi over 4, that should take me back to 7 pi over 4. Right? So, guys, for example, whenever you're working with the unit circle, you can actually just count. You can imagine that you're counting by the fractions. So if I was to count by pi over 4s, I would go from 0 to 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. So to go negative pi over 4, I just have to go back 1/4, right? And I'm here. Now cosecant, I see, is the 1 over the y-coordinate. My y-coordinate being negative root 2 over 2. So this guy should be equal to 1 over negative square root 2 over 2. When I divide a fraction, though, what I need to do is I need to flip the reciprocal. So this is number 1, by the way, that I've been working on. So I have 1 times 2 over negative square root 2, right? So in the end, guys, because it's 1 over a fraction, I basically just get the reciprocal of that fraction. I get 2 over root 2, and it is negative, right, because there's negative there. Now, I can't just leave it in this form, though. Remember, we need to what we call rationalize the denominator. That's where I'm going to multiply this fraction by that square root on the top and bottom. And the reason why we do this is so that we can get rid of the square root from the denominator. So in the end, I'm left with negative 2 times square root 2, negative 2 square root 2, over the square root of 2 times square root 2. When I multiply 2 square roots of the same thing together, I get the whole number. And, you know, what's interesting is that actually, in the end, the 2's will cancel here. Yeah, you see that? And so I'm left with negative square root of 2 as my final answer. Pretty handy. Let's look at number 2. I have the tangent of 7 pi over 3. Now, 7 pi over 3 is actually more than 2 pi. So it's beyond my unit circle. But once again, I can just count by thirds. I can recognize that 7 pi over 3 is actually going to be coterminal with whatever I get if I take away 2 pi, right? Remember 2 pi being a full circle. Well, 2 pi is equivalent to 6 pi over 3. Therefore, 7 pi over 3 should be coterminal with just pi over 3. And what is the tangent of pi over 3? Well, tangent is the y divided by the x. So I look at my unit circle and I see pi over 3 here. And I say, well, y value is the square root of 3 over 2. And my x value is 1/2. So that's going to divide by 1/2. But remember, guys, when I'm dividing by a fraction, I can instead multiply by the reciprocal. So that times 2 over 1. So in the end, the 2's would cancel here, and I'd be left with the square root of 3. Now that was for the, by the way, this was for the second problem, which was tangent of 7 pi over 3. All right, now let's look at this third one. I have the sine of 2021, so 2021 pi. Interestingly enough, y'all, this number, though it is big, is actually not hard to work with because it's a whole number. And all I need to do is think about, well, if every 2 pi is one full circle, I could just keep taking away 2 pi's from this, right? In fact, I could take away the equivalent of 1010 2 pi's, right? Because 1010 times 2 would be 2020. So imagine, guys, essentially, all I'm looking at is, oh, well, I am 1 pi more than a bunch of circles. So in the end, it should leave me over here at pi to be coterminal. And what would be the sine of pi? Well, sine is the y-coordinate. The y-coordinate here is 0. So this guy would actually be 0 for number 3. So this is just a quick little recap of trig evaluation, y'all. So in our class last time, we went over some notes about amplitude and period, as well as with midline. And what I wanted to do was, in this video, since I'm going to be discussing these topics, I wanted to very quickly go over these notes. Now, you guys feel free to pause the video if you are trying to write down these things, but I'm going to kind of go through it a little bit quickly. So first of all, what is amplitude? Amplitude is the height from the midline to the maximum or the minimum of a periodic function. Basically, guys, it is how far up is the function going and how far down is it going. You can calculate amplitude by using the maximum value minus the minimum value. And the reason why I can do that is because the maximum minus the minimum tells me the total distance traversed, right? So for example, if I'm going from 3 to 12, right, my minimum is 3, my maximum is 12. Well, 12 minus 3 is 9. So I know that I'm traveling a distance of 9 units. We take that total distance and we divide it by 2 because, remember, guys, amplitude is not how far total am I traveling. It's how far up and how far down is it going. Period. Period is the length of from one peak to the next, or really from any point to the next matching point in the cycle. In other words, the period is the length of one full cycle. So every time something repeats itself, the amount of time it took for it to repeat itself is the period. So for example, you can see in a sine curve like this one graphed right here, the period is 2 pi because you can see from here, from 0 until it hits 2 pi is when it repeats itself, right? Notice how after 2 pi, it's going to repeat itself going up. You could also find it from a maximum point to a maximum point, right? Notice from maximum to maximum, that's a distance of 2 pi. Or from minimum to minimum, that is also a distance of 2 pi. In class, someone identified that you can actually find the period using from maximum to minimum because they said, well, from a maximum to a minimum would be half of the period. And notice from this maximum here to this minimum here is 1 pi. Double that and you get a period of 2 pi. So there's actually tons of ways in which you can find period of a sine, cosine, or other related periodic function. Next up, let's take a look at our notes on midline. So midline, we said, was the horizontal center line about which the function oscillates above and below. Basically, guys, it's in the name. It's the line in the middle, right? Midline should always be horizontal, therefore it's parallel to the x-axis, and it's located right in between the maximum and minimum because it's the midline, right? You can always calculate the midline of a function by just finding the average of its values, the maximum plus the minimum divided by 2. So for example, in my Ferris wheel here, we saw that the maximum was 168, the minimum was 10. So if I add those and I divide by 2, I get that the midline would be here at 89 meters, right? And that was straight out of our week 3 mastery assessment, I believe. Alternatively, you can actually find midline by, if you already know the amplitude, pretty easily, because if you think about it, midline is going to be the maximum minus amplitude, seeing as the amplitude is just the distance from the midline to the maximum. So you could also have found the midline here if you knew the amplitude by just taking the maximum minus that amplitude, or taking the minimum and adding the amplitude. Now that we've reviewed our notes about what are the features of periodic models, let's take a look at an example where we actually find those features of amplitude, period, and midline. In this example here, you can see that I'm saying that the Earth orbits the sun. Fun fact, it does. In an elliptical motion. Fun fact, it also does do that. Now it asks us to determine the amplitude, period, and midline of a periodic function, which would model the Earth's distance from the sun over time, right? That over time part is kind of implied. So you can see here that in our model, the Earth is going around the sun. And what's interesting is that the Earth is closer to the sun at some points, and it's further away from the sun at others, right? And so what we can do is we can use those values as our minimum and maximum. So you can see there that 147 million kilometers, that's our minimum value, right? And over here at 152 million kilometers, that's our maximum. That's the furthest the Earth is from the sun. So we know our minimum and we know our maximum. By using those two values, I can find the amplitude, y'all. So remember, guys, amplitude was maximum minus the minimum divided by 2. Well, my maximum was 152. My minimum was 147. So I plug that in. I get 152 minus 147 is 5. And 5 divided by 2 is 2.5 million kilometers. Remember, guys, it's important to keep in mind kind of what your units are that you're working in. All right. So now that we found amplitude, what I'm going to find next is actually midline, because it has another kind of easy formula. In fact, you guys will find that amplitude and midline tend to be the easiest ones to figure out. It's just because if you know the maximum and minimum, it's as simple as plugging them into the formula. So how do I find midline? Well, that was the average. So I take maximum and I'm going to add minimum and divide by 2, right? Now, if I do that, I would get 152 plus 147 divided by 2. And if you do that calculation, you will get an average of 149.5 million kilometers. So our midline is 149.5, our amplitude is 2.5. And something that's interesting, guys, if you ever want, you can check your answer by just adding the amplitude to the midline and saying, well, did I get the maximum, right? What is 149.5 plus 2.5? Well, that'd be 152, which is my maximum. What's 149.5 minus 2.5? 147, which is my minimum. So I can actually kind of use that to fact check myself and confirm that I have the correct midline and amplitude. The last thing for us to find here in this problem is the period. And actually, guys, in this problem, I purposely did not give us too much information about the period because I didn't think it was important. You can see here all the days and times and months around the year, but we already know how many days are in a year, guys, right? Say it with me together now. The period of this function will be 365.25 days in a year. You guys tell me you didn't get that 0.25, or did you? Don't lie to me. Now, yes, we use 0.25 because if you guys know about leap years, right? Remember, every 4 years we add a day to account for the fact that a year isn't actually 365 days. It's 365 and a quarter days. And that's just literally how long it takes for the Earth to rotate around the sun. Orbit, sorry, not rotate. So we've calculated amplitude, we've calculated midline, and we've calculated period. Next, what we need to do, guys, is we are going to be introducing what we call the general sinusoidal function. All right. So the general sinusoid looks like this. It's a times sine, and then within the sine is b times x minus c, and then outside is plus d. So what we're going to do is we're going to break down what this all means. So first of all, I want you guys to notice that our base here, our function, is sine. Okay, all of these letters here, a, b, c, and d, these are all just constants, right? They're all numbers that could be in it. For example, instead of having x squared, right, I could have 3x squared. That's what a is representing. It's just any number which multiplies in front of my sine function. Now, what's going to happen here, y'all, is that a is going to represent the amplitude. So if I know the amplitude of my function or of my model, then I know what should plug here in front of the sine. It's literally a one-to-one relationship. And if you guys remember from Algebra 2, learning about transformations of functions, a coefficient in front of my function, so a number that multiplies in front of my function, is known as a vertical stretch. It will make the function stretched vertically. So that is the literal definition of the amplitude, right, guys? Let's look at b here. What does b represent? B is actually this weird relationship. B is going to be equal to 2 pi divided by the period of our function. So if my function has a period of 2 pi, then what would b be? If my function has a period of 2 pi, then b would be 1, right? So b here, it represents a horizontal stretch, right? It represents the function being made wider. And I hope that it makes sense because we're thinking about period, right? And if you guys think about it, right, the period is a measurement of the horizontal distance that our periodic function travels before it repeats itself. C here represents what we call phase shift, aka the horizontal shift. Now this is saying that we did not get to on Monday, and we are not going to, last class, and we are not going to discuss it today. So we will actually, with all of our work today, we're going to leave that C there as just C, and we'll focus on that in the future. Finally, guys, we have D here. D represents the midline. It is a vertical shift. Imagine if I want to move my whole function up or down, I need to just add or subtract outside of it. So that's what D does. Notice that D is adding the whole thing, right? Now, there's one more thing that I want to discuss here. So for a B here, alternatively, we could say that the period of a function is equal to 2 pi divided by that b value. Now, use these two formula actually come from each other, right? If I multiply period over to the left-hand side and then divide b, I end up getting this second one. Now, it's just useful to have them both because sometimes you're trying to solve for b and you know the period. Sometimes you're trying to solve for the period and you know b. So it's just kind of whichever one fits the mood that you're in or the problem that you're solving. And finally, guys, once again, C, I just want to reiterate, we will learn about this in class another time. So for now, we're focused on amplitude, horizontal stretch, and vertical stretch. So the midline. Now, you might still be a bit confused about the various pieces of that general sinusoid function, the general sine function. And so what I've done is I've got together here a Desmos, which models our general function. You can see here I have a sine of b x minus c plus d. And I've broken down the different pieces. So you can see I have a slider for a slider for b, a slider for d, a slider for c. And currently, they're all set to the basic sine function. So you can see here, here's the sine function, and they match up perfectly. So what I want to do is show you guys kind of, as I move these sliders, how does it affect the function? So if I'm to change the amplitude, that's the number in front of my function, what will happen is it'll change how tall it is. You can see here, as I make it bigger, as I make the a value, which, see, a is 4 here, so I would have 4 times sine. Now my function has an amplitude of 4, so it goes up to a maximum of 4, and it goes down to a minimum of -4. Alternatively, I can actually make it smaller. In fact, I can make it negative. So see, if I have a negative amplitude, then actually, this is still an amplitude of 1, right? Because it's going up 1 and down 1. But notice that it's now an upside down version of the original sine function. So it's just kind of something interesting to see with the amplitude. Looking at b had this weird relationship where it is equal to 2 pi divided by the period. So let's see what actually happens to my period as I change b. So let's see what happens as I make b bigger. So if I make b equal to 2, for example, then this currently, what I have written is sine of 2x. You can see they match up. So what happens is when I have a number inside of my function, like which is bigger, it makes the frequency actually more, it makes it a greater frequency. But what that does, guys, is it makes my period smaller. Because, right, notice period is 2 pi divided by that b. In this case, b is 2, so period is just pi. You can see here, from 0 until pi is what it takes for this new function to repeat itself. I'm going to put that back to how it was. What if I make b smaller? Well, if making it bigger made the period smaller, then making it smaller should make the period bigger. So you can see there, my function here from a minimum at -pi to a maximum at pi, that is a distance of 2 pi. And as we said before, minimum to maximum is half of my period. So actually, if I double that, I get that my period is 4 pi. And you can even see here, if period was equal to 4 pi, 2 pi divided by 4 pi would be 1/2. So that's what the b value does. Finally, let's look at the midline here. So d, the midline, which adds on the outside. So what happens when I move my midline? Well, it just moves everything up or it moves everything down. You can see it doesn't change the actual shape of the curve. It's just moving it up and down, right? So, and it's pretty direct relationship. If I make my d value 2, so I'm adding 2, you can see that my midline is here at y equals 2. And finally, we have the c. C we will talk about in the future, but just as a little sneak peek, I'll show you guys what happens when I change c. So if I make c bigger, what's happening? If I make it smaller, what's happening? So you guys can see what's happening is that c here moves the curve horizontally. And this is going to be useful for us in the future because there are times where, like with our Ferris wheel, we don't actually start at the midline, right? See how the sine function starts at 0, 0 with its midline? The Ferris wheel started at a minimum. So if I do this, if I use my c value, I can move it. And you can see that this guy here is starting at 0, -1 at the minimum. And I can mess with these guys to create that model. So recap, the a value in front, if I move it around, makes the amplitude bigger or smaller. The b value affects the period, making it bigger or smaller. And the d value affects the midline, moving the whole thing up or down. Next, what we're going to do is we're going to look at a bit of how do I then take the pieces of information of amplitude, period, midline from a model, like we've been calculating before with our Ferris wheel problem or with that problem of the Earth orbiting the sun, and how can I create a sine function which models it. So in this problem here, we're being asked to derive a sine function which models the Earth's distance from the sun in terms of millions of kilometers over time in days. Notice, by the way, guys, this is important information at the end here. It tells us what the units are that we're working in. In terms of millions of kilometers, that is my unit of distance over time in days. That's my unit of time, right? So if I want to do this, then I simply need to identify the amplitude, my period, which will let me find the b value, and my midline. Remember, we're skipping the c value for today, so we're going to still have the c in there. Previously, we had identified that the amplitude of this function, or of this model, was 2.5 million kilometers. We had additionally solved that the midline was 149.5 million kilometers. Now, my period, we said, was 365.25 days, right? Because that's how many days it takes to go around the sun. So based on what we said before with the b value, we said that b is equal to 2 pi divided by the period. So actually, my b value here is going to be 2 pi divided by 365.25. And I know that that is a disgusting value to plug into your function. It looks gross. It doesn't look right. You're like, Mr. Hobot, can I just turn this into a decimal? And I'm going to say, no, I want you guys to leave it as a fraction. This fraction is actually beautiful. And the reason why it's beautiful is because it tells us in and of itself, it kind of shows us what the period is, right? You can see from the denominator what the period was in the equation. It's like by keeping it in a fraction, we can kind of see where we came from. So in the end, if I plug these in, I said my amplitude is the a value, so I put 2.5 in the front. My midline is the d value, so I add 149.5 at the end. And my b value was, as we saw before, 2 pi over 365.25. So I plug that in here. And I'm leaving the c inside there. And this function here that we've created is actually going to model the distance of the Earth from the sun over time. And what we'll be able to do with this model is I could then use it to predict the distance at any time. Right, guys? The reason why we create models is to make predictions and make generalizations. So I'd be able to know at this June 21st time exactly how far that is. I could know exactly how far I am on March 21st. I could know exactly how far I am on December 21st or September 23rd, and not just at the minimum and maximum. Now here I have on Desmos, I've graphed that function that we just derived for the modeling of the distance of the Earth from the sun as it orbits. And you can see that this guy has a midline at 149.5, right? See, that's the middle line. It goes up to 152, which we said was our maximum. It goes down to 147, which was our minimum. And what you should find here, guys, is that actually the distance from one maximum to the other maximum. Now, I know those are kind of weird numbers, but that's because of the decimal we're working with. Oops. So from one maximum to the other maximum, is this a period of 365.25? Well, we got 91.313. 91.313. And the other maximum point here was 456.563. If I subtract those, you can see the distance between them is 365.25. So this crazy function that we derived actually is modeling the distance of the Earth from the sun over time. So now here's our final part to this video that we're going to do, y'all. I just want to do one more example, and we're going to go back to our Ferris wheel model. So we're going to once again derive a sine function in this form. Now, if you guys remember from us doing the mastery assessment, or from our work talking about the mastery assessment, or just in general as I've talked about this Ferris wheel over and over and over, the amplitude of this Ferris wheel is 79, and you can see here we actually have been given the midline, and I could know the amplitude was 79 by just taking the maximum and subtracting the midline. So my amplitude for this is 79 meters, right? Remember, guys, notice that I'm working in meters over time in minutes, so I should use those units. My midline was given to us 89 meters, and my period is 30 minutes, right? Because remember, half of it was 15 minutes, so the whole thing should be 30 minutes. So if my period is 30 minutes, then my b value is 2 pi divided by 30, which is going to be pi over 15. And so if I plug these all in, 79 goes for A, 89 goes for D, pi over 15 goes for B, and I get 79 sine of pi over 15 x minus c plus 89. And really quickly, what we're going to do is we are going to take a look at that on the Desmos. So here it is. And so here you can see that my function is 79 sine pi over 15 x minus c plus 89. And so this function here has a midline at 89. It has a maximum value of 168 and a minimum value of 10. And something that you can see is that from one maximum to the other maximum is 30 minutes. So it has the right period, it has the right amplitude, it has the right maximums and minimums, it's got the right midline. It's exactly a model of the height over time as you go around the high roller Ferris wheel. So to recap what we have learned in this video so far today, y'all, we determined the amplitude, the period, and the midline of periodic models, and we discussed how you find those. We identified the connection between those features of amplitude, period, and midline, and the equations of sinusoids, right? We looked at the general sinusoid function, and we looked at how do amplitude, period, and midline affect this function. And then finally, what we were doing is we were using that function to derive models of periodic behavior, such as our Ferris wheel or the Earth orbiting around the sun. So hope you were taking some good notes. Hope you learned something today, and I will see y'all in class next time.